All right, the first chapter of every programming book tends to be the same thing, something like history of programming or history of computers, stuff like that. So we're probably not going to spend a huge amount of time looking at the PowerPoints for chapter 1, but we'll give it a little bit of justice. So what is a computer system? It's a combination of all the components required to process and store data using a computer. All right, sounds good. What is hardware? It's the equipment associated with the computer. You can kind of see what I mean, right? Software. All right, what's the difference between hardware and software? Hardware you can touch. Software you can't. Software consists of programs. What are programs? Programs are instructions written by programmers. So what is programming? It's the writing the programs. Broadly speaking, people divide software into several different categories, such as application software. I'm going to launch Word, create a document. I'm going to use Excel, get a load of Chrome or something like that. Games are considered applications. And then there's system software. The system software is like the operating system. You run Windows and you need to format a drive. You find a drive format utility. Linux or Android, iOS. Those are all system software. Now this is actually worth looking at. Computer hardware and software basically accomplish 3 major operations. Input, processing, and then the next one should be output. Pretty much that's all computers do, all programs do. If you're playing a game, it's getting input based on your joystick or your keyboard strokes or whatever. The processing, it's updating the position in its mind of all the characters that are supposed to be displayed on the screen. And then the output, it updates the screen to show you the new positions of the players. Or the input, it asks you for your weight and your height and your age and something like that. And the processing, it performs some calculation, right? And the output, it saves that data to disk or displays it on the screen, right? Quite often, it keeps looping, right? Keeps asking for input, keeps doing some processing, keeps doing some output, right? Because a game that just showed you like one frame, for 1/50th of a second and then quit, that wouldn't be very much fun. It has to keep looping. Or if you're writing a program that calculates, somebody's payroll, it'd be really annoying if you entered all the information and it showed one person and then the program quit and you had to run it again to type in the next person. No, you'd want it to let you type in person after person after person until you close the application. So what is a programming language? It's what you use to create the program, the series of instructions. And I told you that I call it source code or, your program or your script. Well, this textbook's calling it program code. All right, whatever. Source code just means that it's the source for the program, right? So if we're going to be a little bit more generic, we'll call it program code. I'm never going to mess you up and give you like 2 different terms and then tell you that you only have to pick I'm not going to try to say, is there a difference between source code and program code right now? I'm not going to ask a quiz question like that. I'll make it pretty easy to pick out, that I mean both of them to mean the same thing. Writing instructions is called coding the program. Coding, it's kind of a weird word. It makes it sound like you're trying to, normally what do you use code for? To make a secret message that nobody can read. Well, it could be that somebody thought that, program code looked like a secret message, but really we want to make our programs as easy to read as possible. Now back in the olden days, people used something called assembler. Yeah, that kind of looks like code, right? That's not real easy for us to read. We can't tell that it's looping and setting A equal to 2 and B equal to X plus Y, right? We see some English words here and there, but it's pretty arcane. So maybe that's where the term coding came from. Anyways, it's just the act of writing the instructions that the program's going to follow. And then we have languages. The programming language is what you use to create the program code, and we have several different ones. Like I said, the textbook isn't real Python specific, but it would have been nice to at least have a feature here, right? And then the syntax. We're going to be fussing with syntax a lot. Those are the rules governing the way the language works. It's the grammar of it, just like English has grammar, right? In English, we tend to put the adjective in front of the word. I drive a red car, right? Whereas in Spanish, it's kind of flipped. You put the noun and then you put the adjective, right? So, you know, I don't know the Spanish terms for, you know, a green tractor, but, you know, it would instead be tractor green, right? That's how you refer to things. The adjective follows a noun, whereas in our language, you know, they precede it. And English also has kind of another funny feature where, you know, you can have multiple adjectives for a noun. You know, I have a big white truck. Well, why did you say it was big and white? Why didn't you say I have a white big truck? You could. But typically, the things that are closer to the noun are the things that are more important, more integral to its classification, right? White truck, right? That's more important than the fact it's a big truck. The way our minds work is we think of the color of the thing as being more integrally tied to it than the size. You know, that's why it's Clifford the big red dog rather than Clifford the red big dog, right? Dogs change in size as they grow, so I guess, but they don't typically change their color until they get too old and their hair turns gray. So the examples of grammar in a programming language include things like, how do you specify blocks of code? What is a block of code? This textbook calls it a module. So for example, you don't have to type along with this. It's not actually part of the program. I'm going to just type in some notes here. Just as a reminder, when you launch idle, just like I did, I went down here and I typed in IDLE. Don't start typing your program in here, right? If you see me type in, you know, x equals 3, y is equal, right? That's not the program. You have to do file new. And then you're ready to go. Okay, so examples of grammar, examples of syntax. In some programs, you divide code up into blocks using braces in some programming languages, right? Instead, in Python, we use tabs. Now, those other languages also let you use tabs, but they're not necessary. And I'll give you an example. We could, in some of those languages, do if x equals 3, curly brace, y equals 4. You really don't have to type this, guys. You know, z is equal to y plus 2, you know, and then we're going to print z to the screen, right? This is why I'm saying you don't have to type this, because we're not learning this particular language that's an example of. All right, so this is C-style syntax. And in particular, this happens to be C++. In Python, we would probably write it like this. If x equals 3, colon, y equals 4, z equals y plus 2, and then we'd have a print statement. Just like that. Okay. So, what's the difference? Well, in these C-style languages, the condition has to be put in parentheses, right? It doesn't break Python to put it into parentheses, so you may see me slip up and accidentally do it, but you don't have to. And if you don't have to, why bother, right? Maybe you think it makes it easier to read. I kind of like it just because a million other languages do require the parentheses, but it's not necessary. In these C-style languages, you have to have these curly braces that mark off your block of code. In Python, you don't. If you put a curly brace there, it's going to count as a syntax error. If I did that, that'd be a syntax error. So I'm not going to do that. How does it know when a block of code begins? Well, Python wants a colon there instead. So every time there's a colon, we start tabbing all the lines in that block afterwards. That colon serves the purpose of the curly brace. Well, then how do we know when the code stops? There's no curly brace to tell us when that code block stops. Well, it's just the next line of code that is unindented. So there we go, right? These are the same thing. This marked the end of the block here. We didn't have an end of block marker, so the programming language just assumes that the next time it hits some unindented code, it is the end of the block. So everything that's tabbed is part of the block. Everything that's between the curly braces is part of the block. Since we have these curly braces to us, the tabs aren't important. They're important visually, but they're not important to the way the computer understands the code. So if you mess them up, right, there's nothing wrong with that. The code will work just as well, even though it looks sloppy. Works just as well. Okay, so something else. We see these semicolons. In the C programming languages, almost every line, except for a logic line like if, ends in a semicolon. Our language doesn't need semicolons. Now, I think we can get away with putting semicolons on it without causing syntax errors. We could try that out, but it's absolutely not necessary, and most Python programmers don't do that. Since we have these semicolons, we can do things that you can't do in Python. Like, what if I wanted to do that? Well, that doesn't make any sense, right? Y is equal to 4 is equal. You can't do that in Python. Well, maybe you can, but it's not. But there's nothing wrong. It's very, very common for C programmers to go ahead and embed multiple lines of code on the same line. Now, you can kind of tend to avoid that because it can make the program harder to read. So most people don't, but you can. And then you'll notice that, the displaying of something to the screen is done with completely different keywords. Print here instead of cout, which stands for console output. What does ENDL stand for? It stands for end of line. Well, Python goes to the next line automatically after a print statement. End of line just means like hitting the enter key, the return key on your keyboard. So it would print out Z and it would go to the next line. Well, the print statement does that automatically, so we don't need an ENDL. So we see two different examples of syntax, and if they're botched, the program won't run. If I'm missing a semicolon up here in C++, in C, it's not going to run. If I tab this wrong, even though it looks right, kind of looks right, not going to work. Here's a, there. That's not going to work. The tabbing is wrong. Looks pretty close. Now, C++ does not care one whit about tabbing. But since it doesn't use the curly braces, the tabs are very important in Python. That's just an example. Now, we're not going to really use curly braces as part of our blocks ever again because I'm almost never going to be giving you C++ examples. They're in the book, and you'll see examples of them throughout the book. We don't need those examples. So mistakes in a language usage are called syntax errors. When I left that semicolon off there, if we were writing some C code, that would be a syntax error. Slightly more subtle syntax errors could be something like this. This is legal code. Age equals 32. 32 equals age is not legal code. The program would not run. Well, why? It looks good to me, right? We're telling ourselves that, and we're telling the computer that the age variable is equal to, well, it's just that all the programming languages have decided that the left-hand side has to be the variable, and the right-hand side has to be the value. And if you try to flip it, it's just not going to work. It's just the syntax of it. And a million languages follow that syntax. So one of the things you get familiar with doing in this programming language, or in any programming language, is interpreting the errors when they come up. I'm going to do that thing right there. I'm just going to try that line of code. age is equal to 30. You notice that I ended my multi-line comment there. I started my multi-line comments with the triple quote up at the top. Really, I wish I had put, the class name, maybe the date, and maybe my name. And then what lecture it is, lecture B, something like that. Comment block. I really, really, really want you to turn in your homework with a comment block up at the top. Might get to the point where I start rejecting assignments without the comment block. That seems kind of picky, but I really want you to do that. That's professional. Okay, so here we go. This is good syntax because the left-hand side is the variable. The right-hand side is the value. And if we swap them, we're going to get a syntax error. All right, now I'm going to save my work and run it to prove to myself whether that works or gives me a syntax error. So I saved it. I went to my correct directory. Like I said, never save things into that directory that says, well, now that I've done it so fast, I can't demonstrate it to you. Do that again. Just right. If I'm typing something here and I want to save it, by the way, never save your shell output. You can override your py file and lose your py file if you do that. What do I mean? When you open up the shell and you start typing in commands here, if you then do save as and you saved it as lecture b.py, boom, your lecture p.py file is gone. I'm just doing this to remind you, never save it into the Python 37 directory because this is system code. I really have to see what these things are. We're going to find out what's in that file. Huh. Don't look like hello world. It looks like a counting loop. How about this new file? Well, it's 0 bytes long. How about this one? All right, I'm going to delete those things. We don't need those in here. Anyways, never save anything into the system directory. Why? Because you can break Python. You can make it so that your code just flat out, as soon as you launch Python, it dies. We don't want that. Okay.
Can you use it to reinstall it?
That's a way of fixing it, right? That's one of the likely outcomes. Or you might be able to open up the Python directory and see the offending file, right? You see something out of place, right? You see a py file there where there shouldn't be. Okay, so I relaunched idle. I don't want to have to go to the trouble of finding it again, so I'm just going to do recent files and pull up my lecture B file, recent files. Okay, so I'm ready to demonstrate the syntax error. I run it and it yells at me. Can't assign to literal. Well, that's pretty cryptic, right? That's not telling us what's wrong. Well, it is telling us what's wrong. It's just using language we haven't learned yet. We have two things here. We have a variable name where we're putting some data, and then we have the data itself. This number is called a, and I don't know who made up the term, I'm sure it dates like to the 50s, is a literal. The only way I can remember that is I think it's literally typed into the code, right? I didn't ask the user for the age, or whatever that number is supposed to be. I didn't, read it from the disk, or, it's not input, it's actually, quote, hard-coded, end quote, into the program. Why is it called hard coding? Because if you wanted to change it, you'd have to edit the programming. Now, maybe you've heard the terms like, firmware, something like that. You have some kind of place where your code is actually burned in to a EEPROM chip, electrically programmable ROM, ROM standing for read-only. It's a real drag if you have to change something in your EEPROM, because you can't just open it up with a text editor and make a change. You have to actually download something that's going to update it and all that. So things that are hard-coded are just in there until something changes it. So this is called a literal, or a numeric literal, because there's other kinds of literals as well, right? Like if I do name is equal to Jeff, well, Jeff is a literal. It's hard-coded into the program. So that error message is telling me that you can't store a value into 32. It's kind of like this equal sign is an arrow, right? Like that. Put 32 into age. Okay, yeah, computer knows how to do that. Put age into 32. No way. That would erase the number 32, and the universe would be fundamentally, fundamentally altered. Okay, I'm kidding about that. But what does it change? What does it mean to try to change the value of a number, right? I can't just suddenly change the value of 12. Can't change the value of 32. So this is a syntax error. That's why we were getting that message that said cannot assign value to a literal. That was our syntax error. And you see why I said you don't have to type everything along, because I make a lot of intentional errors, and then I revise it, and then I revise it, and then I revise it. Now, when I'm actually wanting you to type along, I'll make it real clear. On the other hand, there's nothing wrong with taking as many notes as you want if it helps it burn it into your brain. You just gotta have to be aware that I'm going to be hacking and slicing and dicing these little things and not taking much care to make sure that I type slowly enough for you to follow along if it's part of my expository text, if it's part of something that I could have put into a PowerPoint if I wanted to rewrite the PowerPoints. All right, so can't assign to a literal. And well, then I would need to fix that. So this is good syntax. That's the required syntax. This is bad syntax. The error message would be can't assign to literal, right? And so the rule is that the variable, the word, has to be on the left-hand side. And the value has to be on the right. What is a literal? It's data that is hard-coded into the program. Now, when I'm typing sentences like that, I don't care if you type them in, right? Good. It's good stuff. You can always go back and review the notes. If I'm going to the trouble of typing English text, it's because I want you to remember it, right? So just remember it in the way that best makes sense for you. And I word things a little bit differently than the book does. But if you give me a textbook definition for what a literal is, I'm not going to count you wrong, right? I've already told you that during your exams they're open books. So if I ask what a literal is on an exam, and and you search the book and you find a definition in the textbook, I'm not going to count you wrong. I just give you definitions that I've read a bunch of programming books and they all say something slightly different, so I try to give you one that's kind of centrally located, as well as when we get the PowerPoint, we'll see what the book called it. So in this case, the literal was 32. There's more than one kind of error, by the way. There's syntax errors, and then there's logic errors. A logic error is when the program runs because it doesn't have any syntax errors, but it doesn't do what it's supposed to do. Like, what if you're playing Pac-Man and every time you hit the up arrow, the Pac-Man went down, right? That's a logic error. It's not doing what you want. What if it's supposed to turn the AC on when the temperature gets, above 100 degrees, but instead it waits until it's 120 degrees, even though you programmed it to do 100 degrees? Well, that's a logic error. It's doing the wrong thing. What if it's supposed to be converting to Celsius, but it doesn't? That's a logic error, right? Computers follow your instructions very specifically, and if you tell them to do the wrong thing, then they're going to do the wrong thing. If I told you to go to Walmart and I said that it was on the left side of Sooner rather than the right side of Sooner, you'd probably get there and notice that that great big building was on the right and you could handle it. However, the computer would not be able to handle that. What do y'all think of self-driving vehicles? You think that's a good idea? Wave your hands. You think it's not maybe the best idea? Wave your hand. Okay. One of the reasons I think self-driving vehicles are bad is a huge part of our economy is just based on delivery drivers, right? Truckers make a good living at it, right? And you don't have to have a college degree to become a trucker. Delivery is a big portion of the economy. And if you find a way, and companies would love to do this, fire all those people and replace them with self-driving vehicles, or vehicles where somebody just has to sit there, right, and press a button to go somewhere, and so they don't have to be qualified, right? They're going to be happy to do that. And lots of people are going to be out of work. I'm not really digging it. Also, the fact that they tend to steer, you know, into oncoming traffic or whatever. Well, I sound like a horse and buggy person, you know. Yeah, back in my day, we drove our own cars. So,
Well, you also have the issue of the computer having to make decisions.
right,
Like if there's an accident going to happen, do I veer to the right and hit the old lady walking, or do I protect my driver? Do I hit the bus full of children? Like,
right, yeah.
what minimizes the risk? And
Exactly, right. We're trusting the computer to do stuff. And y'all have used computers enough to know that you can't really trust computers very much. You know, they crash, they make wrong decisions. And yeah, I can fully accept that computer-assisted driving would probably be actually safer once you get to a certain point. But, you know, also don't like the idea of all of us just being sheep that get, you know, herded into a vehicle and we're not in control of it.
when you said the keyword assisted,
Right, right. Assisting is okay, right? You know, if I'm about to slam into the car in front of me, if it started applying the brakes for me a little bit to try to save me, I might appreciate that. Okay, so computer memory. Inside your computer, there's a whole bunch. Sorry for the people who are watching this, writing on the screen. You can't see it. You know, places in the computer which has got just whole bunches of places where zeros and ones can be stored. Now the zeros and ones get translated into higher pieces of data, right, like numbers and names and music files and images. But overall, all you have are bits. That's the nickname for them, an officially accepted term for them. And a bit can either be a 0 or a 1. That's the smallest unit of information in a computer. You know, even before chips and stuff like that, you had bits because you had vacuum tubes, right? And if the tube was glowing, it was a 1 or a non-zero value. And if the tube was not glowing, had no current through it, it was a 0. And even before that, you had mechanical computers where relays, you know, would connect or not connect, right? And if the circuit was closed, current going through it, that's a 1. If the circuit was not closed, that's a 0. And ultimately, you could go back to some kind of a Bacchus or something, right? Where if the stone was on this side, it meant nothing, and if the stone was on this side, it meant something. So you have something or nothing. Now these zeros, right? You know, if I had, you know, these can be translated into numbers. And for ease of use, because we don't want to look at a page full, you know, or a book full of zeros and ones, then people find ways of converting these into schemes where they're actually represented by numbers. So this is an 11. This is a 13. Do you care? That's a 15, and that's a 2. After a while, you're going to learn what those numbers mean and how we got them, right? So if I wanted to look at computer memory, I'd rather see 11, 13, 15, 2 than this stuff. Then there's another naming system where these get condensed down into single letter equivalents. This is known as hexadecimal for reasons I'll show you. This is called decimal, you know, numbers between 1 and 10. And this is the binary. All right. Big deal. What do we need to know about this is that each 8 bits are called a byte. You've heard of bytes. You know, I bought my new iPad and it had a whopping 512 gigabytes of RAM. Right? Gig, meaning billion, more or less. So, got a billion, or 5 billion, or, you know, 512 billion, whatever your gigabyte is. That sounds a little bit too large. Yeah, I think that's probably a little bit too large. 512 gigabytes for one of our devices is an awful lot. That's more hard drive size. Anyways, right? And so your computer memory is just a series of bytes. Starting at address 0 and going out to as many bytes as your computer has installed. Right, I bought a 4 gigabyte laptop. I'm not planning on running any really cool games, so it's just got 4 billion different places where these bytes can be stored. if I want to store my name in it, in order to print my name out, somewhere in here, there's going to be a J stored, followed by an E, followed by an F, followed by an F, right? Continuously. It doesn't matter where. The computer keeps track of that, and the program keeps track. You know, this could be memory address 2,300,000 and 200, right? Yeah, doesn't matter. But then the next one, the next letter is going to be at 2300271, right? And then the next one is going to be at 230,027, right? They're just going to be contiguous in order to indicate that, you know, this is a block of data. And numbers are stored in some kind of strange little syntax, which we'll talk about. You know, if I have the numbers, you know, if I say I'm 75 years old, that has to be converted into zeros and ones. In some ways, that's not exactly obvious until we learn about it, right? But anyways, those might be stored in a completely different area. So that's what computer memory is. It's just a series of things. Now those zeros and ones, you know, we have lots more kinds of memory than just random access memory, right? You buy a DVD, there's all these pits burned into it, or, you know, various shades of colors or something like that. If you have a magnetic drive, there are places where there are charges and then there are no charges, and that represents the zeros and the ones. You know, good old punch cards. You grew up programming in the 60s, you had punch cards. Those are even before my time, right? And the little holes in the cards represent, you know, data, because you could either have a hole or not a hole, right? So, zeros and ones is what it all boils down to. And we'll spend a part of a class period talking about translating zeros and ones into real data that we understand. Computer does it for us, right? But we need to understand just to make ourselves better programmers. So that's the computer memory. And then there are permanent storage devices. Non-volatile memory. Random access memory gets wiped out when the power is off. Non-volatile memory is supposed to maintain its state even when the power is off, right? Your little SD cards, right? You take pictures with your camera or whatever. It gets written out to some flash card device, you know, so that you can eject that and put it into another camera in your computer or whatever. That's non-volatile memory. You don't want it to get erased just when you pop it out of the camera. Same thing for hard drives, right? You don't want your hard drive to lose all of its data just because the computer was shut off. So that is not random access memory. Now the term permanent is slightly optimistic, right? You know, 70,000 years from now, are we going to be able to pick up that hard drive or that flash card and get it to work? Yeah, but you know, we'll call it permanent. So nowadays in your phones, you don't have hard drives and stuff like that. Instead, you just have some kind of flash RAM that's built into it, right? A lot of phones don't even have slots where you can insert an SD card. I think they all should, but I don't own Apple, so I can't make them do it. Another key thing is the compiler or the interpreter. That's the thing that turns the source code into what's known as machine language. Now this is kind of going backwards because it's not telling you what machine language is. That's okay. We're going to be talking a lot about compilers. We're not going to talk hardly any about machine language, so this is the more important term for us. What is a compiler? A compiler is what turns this stuff, A equals 3, B equals A plus 2, into computer instructions. Right? Those are not computer instructions. Yes, sir.
So the question about, you were talking about the memory a moment ago. How does it work for like wireless storage devices such as cloud or?
Very good question. What does a cloud mean? The cloud just means a hard drive stored in some other place other than here.
It's a central location.
It's a central location with a huge amount of redundancy and backups and capacity. Right. So, you know, Amazon offers cloud services and IBM offers cloud services and stuff like that. It just means that there are servers serving up hard drive space that can be accessed over the internet.
Okay.
But, you know, I'm sure you have the idea of local servers, right? You know, you install a network, you know, drive out on your local machine. But that's not really a cloud because you have to have an active connection to it, and you know it's managed by yourself. But it's just a fancy term for network servers installed somewhere else. They give it a magical name because it's marketable. So these are not computer statements. And I'll get into that. These have to be translated into something that the computer understands. It has to be translated into a series of what are known as opcodes, which we absolutely do not care about, which control the chip directly, right? We have to tell the chip ultimately to copy the number 3 into a certain place into our RAM so that we can do something. And then copy another value, do some math, add 2 places in our RAM to something else. We'll get back to that, but this is not machine language. These are not opcodes. This is some English-like text, some algebraic text. It's a programming language. And it's not going to do a dang thing. As far as the computer's concerned, we could have just written this on the wall, right? You know, or written it on a piece of paper or in a book. It's not going to make the computer do anything, writing something on the wall. Instead, it has to be translated into those instructions, those binary instructions, the machine language that will then run the chip and make stuff happen. So you can have source code, which is, in this case, we're going to write in Python. And then we run the compiler or the interpreter. Those are very similar things. I need to put my triple quotes back into place. As long as everything's green, I know we're good. What would happen if I left, you know, these up here? It would get a syntax error when it got down here, right? Because that's not computer code. That's not a programming language. So I'm still inside my multi-line comment when I'm typing my notes. Okay, and so the compiler interpreter turns the source code into machine language. I'm going to say opcodes just to be all fancy and act like I'm a, you know, electrical engineer who knows how to create chips. Without this step, it won't run. Without compiling it. So when it turns the source code, the fancy word for that is compiling. So the compiler compiles the source code into machine language. By the way, I absolutely love questions. You become my favorite student when you ask questions. So the rest of y'all need to step up your game. I'm kidding about that, but you know what I mean. I love questions because I know that if one person asks a question, then it probably means that there were 5 other people wondering it. And if nobody asks a question, there's probably still 5 people wondering about it, and they're not getting their answer. So after it is compiled, the program will run, or we got to use a fancy term, execute. Nice violent language. We're going to execute the program. We run the program. Without this step, it also doesn't run. The compiler just turns it into machine language. It's like I give you a French document and you turn it into English. Well, you transcribed it, you know, you put it on a piece of paper as English, but until, you know, the president reads the speech or, you know, you give the instructions to somebody, it still doesn't do anything. It's just a piece of paper with some English words on it. Same thing for machine language. It's not until then the program is run, executed. It gets loaded into the computer's memory somehow, and then the computer starts following it step by step. And that's when it actually is doing something useful. So typically you write the source code, it gets compiled, and then the program gets run. Now the different, you see the term compiler and interpreter, and the book talks about both things. The difference is that a compiler ultimately saves the results to disk so that you can email somebody the results. Right? It makes like an executable, a .exe file. Or if you're a Mac user or a Linux user, it makes an app. you know, .app file, or if you're, you know, creating an Android application or something, right? It makes a file, whereas an interpreter runs it right on the spot. Just like when we had the shell open. It's running it right on the spot, right? If I type in print Joe, runs it on the spot. It does it immediately. It doesn't save a file. It doesn't make an exe that you can email to, you know, your friend and then have the word Joe on the screen. That's what a compiler does. An interpreter runs it and just immediately, as soon as it's typed in. But what's going on underneath the scenes is very similar for both, right? They both have to do the translation into the machine language. It's just that in one case, you know, it gets stored as a file, and in another case, it gets run immediately. So the terms are kind of synonymous. So most of the time, I'm going to use the term compile. I'm going to run my program is usually what I say, but the intermediate step is it gets compiled before it gets run. If I wanted to be all technical, I would say it gets interpreted before it gets run. We boil things down, you know, into more and more precise terms, and then we back up. Let's just use the term compile, you know, or use the term run. We're going to kind of use those synonymously, even though they're not exactly the same thing, right? The program has to be turned into machine language before the computer can run it. But I have to turn my car on before I go to work. But I don't tell you I'm going to go start the car, you know, and then drive, right? You know, I just say I go to work. And I don't mention all the steps, you know, that happen in the intervening time. I'm not going to say compile. I'm just going to say I run this.
So when you say like a Word document, say the report, all the information that you say gets transferred into zeros and ones into binary for the computer.
Exactly.
And so then when you go to reopen the file, the computer compiles that information of zeros and ones, translates it into legible information that we can see.
Right.
And then runs the program once you.
Well, if it's a document like that, then there's already a program running, right? Word is already running. And so what it's doing is it's opening that file, converting the binary data into something that it can display on screen.
So
and that,
more of an interpreter.
Yeah. And so that thing that's being displayed on the screen, you know, it could be anything. It could be, you know, a music file that is going to start playing, or it could be a picture that is going to display, or it could be text on the screen. But there has to be some kind of agreement as to how those zeros and ones represent text, right? All Word documents and all text editors and whatever have to agree that if an A is written out, then it has to be this series of zeros and ones. And that if a picture has got, you know, a block of red, it's got to know exactly how to do it.
So then, like RAM drive, your random access memory, is it, if you were to watch a video on YouTube as it's buffering, would that be considered
right?
Temporary.
Yeah, as it's right. If you're watching a video, it's got to be loaded into RAM, and yeah, you're not doing that on purpose, you know, but it happens, right? It's got to be, good term, buffered, meaning that it writes down all that information, or reads in all that information into the device's RAM, so that the video player can then actually show it on the screen. And some applications, you know, Netflix lets you download some of those things to the permanent storage so that you can watch it, you know, even when you're driving the subway and you don't have an internet connection.
So when that data is transmitted, because it's wireless over internet, and the computer starts buffering, is it transmitted as binary, or does it have to convert it to binary?
It's being served up as binary over the network connection.
Okay.
Yep, exactly. Everything is zeros and ones. All of our internet connection, everything going over, you know, the radio waves. And you know, your Wi-Fi router, all of that is ultimately zeros and ones, and the two devices have to agree that a specific series of zeros and ones is this kind of picture, or this series of letters, or something like that.
Okay.
That makes sense?
Yeah, so essentially you're just, a computer basically just transfers information from one thing to another.
Exactly, right.
Language we understand. Kind of like you would radio frequency, it's the same kind of concept, turning radio waves and frequencies into something.
Right, yeah, because, you know, if you get in your car, there's no way, you know, there's some abstract radio thing, you know, in the spectrum, you know, a signal, you know, the decrease and increasing strength. It's not music, it's not words, right? It has to be, the radio turns it into that. Yeah, and if you have a satellite radio, it works completely differently. It's getting a series of zeros and ones that it converts into that stuff.
Oh, okay.
I hope that's true
So
because
for
I just said
satellite
that.
radio, then it's not actually a frequency, it's just basically a binary code telling you what it is.
Right, right. And since it is being communicated via some kind of, there is a frequency involved, but it's
Right.
but it's being sent, as zeros and ones to it,
It's taking the frequency and
just
then
like cell phone
transmitting
data.
it over, instead of your car transmitting it into the sound.
Right.
It's doing it for you and sending the signal.
Yeah. So a program with syntax errors cannot execute. So we're going to say that there's two different kinds of errors. That there are syntax errors and that there are logical errors. And then I'm going to throw a third one in for you. So the syntax errors are mistakes in the grammar. The program won't run or will stop running when it hits one. It's a failure of it to be compiled. Right, when I typed in 32 is equal to age, that's bad syntax. It couldn't be interpreted or it couldn't be compiled. Right, that's not going to be able to be turned into machine language, so it just fails. That's a syntax error.
But when you're working on Word and it pops up an error message, you need to close the program and reopen it. That would be a logic error.
Yeah, it would be, but I'm going to give you an even more precise term for that I don't recall if the book tells you. Yeah, exactly. So you have a logic error, which is a mistake in the logic of the program. Program runs, but doesn't do the right thing. Then there's a kind of a third one that's not necessarily a logic error, called a runtime error. A runtime error is when the program gets into a state where it can't continue. Right? You eject the hard drive as it's trying to save the file. What's it supposed to do? Right? It can't write it out. It's not a logic error. It's not the program's fault that you ejected a drive. Or, you try to establish a connection to a server and the internet's down, right? Or you accidentally divide by 0, which is, not a valid thing to do. What does it mean to divide 1 by 0? And, our minds may say, well, anything divided by 0 ought to be 0, but mathematically it's defined as, an invalid operation, and anything divided by 0 is infinity, or it's an invalid state. So runtime error is the program reaches a state that it cannot handle. And then when you get that most lovely of errors, program has, encountered an error and must be quit, it has hit a runtime error.
So how do we fix that? Getting a better hardware then?
It's just that it has done something wrong or gotten to a point from which it cannot recover. Not necessarily a hardware error. Dividing by 0 is not a hardware error. Running out of RAM, it's not necessarily a hardware error. Everything's working perfectly. It just got into a state from which it cannot recover. But yeah, hardware errors would also produce runtime. And sometimes the operating system kills your program because it detected it doing something that it shouldn't be doing. It's trying to write to RAM it doesn't own, right? And if the programs are able to write to RAM that, it's not supposed to, then they could interfere with each other, right? I could have, some network security software running on my machine, and I could have, this application that I downloaded, and it might be trying to make changes to, to RAM that it's not allowed to do. And in that case, the operating system should detect that and kill it. And that can be one of those, RAM, Word has encountered an error and must be shut down. Word was trying to write to a place in memory that it wasn't supposed to. Now, it's not because Word is being malicious. It's just a mistake in the program, some kind of runtime error, logic error that led to it. So a runtime error, textbook might call this a subset of that, but they're really two different things. However, good logic might be able to preclude runtime errors, right? If I write a program and it just expects that the hard drive is there and it crashes if it doesn't, well, it hit a runtime error, but some good logic would have been able to fix that, right? It didn't have to crash. It could have just popped up an error message, right? And then let the user pick another place to save the data to. So good logic can usually fix runtime errors.
So if you're setting up a program in Python and you get down towards the end at a point where you put like x equals 1 over 0 and then you run the program, will it give you a syntax error because you put 1 over 0, or will it actually run the
It'll
program
run
up
it.
until the point it analyzes x equals 1 over 0?
Right, because it doesn't know. Well, I mean, maybe it knows. Right. If we did this, the compiler maybe ought to be smart enough to know that that's a syntax error. But what if it's a little bit more subtle? X is equal to 0, y is equal to 3, z is equal to x divided by y. Right. It's still going to get to the point. Whoops, sorry. Right, y divided by x. It's still going to get to the point where the program is going to crash because it divided by 0, but the compiler didn't really know that was going to happen. Or what if it was even an input statement here? We asked the user to type in a number. There's absolutely no way that the interpreter, the compiler, would know in advance that we were going to type in a 0. And so it has to wait until it gets to that line before it can crash. And it will. 0 division error, division by 0. We've been talking about errors and stuff. Suddenly we're changing into the parts of a program. The variable is a named memory location whose value can vary. Variables are incredibly important. Variables are pretty much all that we do. That's a variable. That's a variable. That's a variable. Why do you need variables? Because otherwise, back, do you remember our good old place where I said, then I had JEFF and the memory address was 2,300 and 1,272, whatever, right? Conceivably, I could say memory address 2,300,000 is equal to Jeff, right? But that's absurd. There's 4 billion memory addresses in our computer. There's 8 billion memory addresses. We do not want to address them by number, particularly because these applications, move around in memory. What do I mean by that? The first time you load up your computer, you launch Word, and then you play Fallout. Well, Word's going to be located in the first block of memory, and then Fallout's going to own the second block of memory. The next time you turn your computer on, you play Fallout first. Well, all the memory addresses are completely different, right? They're stored higher than the memory addresses that Word is going to use. So we don't want to use absolute numbers. And this is what they did back in the old days, in the 40s and the 50s, before programming languages were invented, and maybe even after that. You addressed RAM directly, because those computers only ran one program at a time, right? And then after they ran the program, they were just done. After it calculated all the artillery, tables and stuff like that, or made the calculation for, the atomic bomb reaction or whatever they used computers for in the 40s, then it was just done. And it was okay for them to say, I'm going to store this number into memory address 1, this number into memory address 2, and so on. But we don't want to do that. So a variable is a named place that represents memory. This is really important. I'm going to type it in all caps. A variable is a named location in memory. We're going to get a little bit more specific and say that a variable has 4 parts. 3 of them really matter to us and 1 does not. Variables have names, right? When I say age is equal to 32.
By putting in a variable, we're telling the computer where we want it to be saved.
Well, not where we want it to be saved, but we're giving it a name, right? And the computer decides, the language decides where it's going to be saved.
So does it save the information numerically? Does it just go through?
Yeah.
Okay, this is the first piece. This is 1 through 10.
Right.
This is,
Because if I live, at 123 Burning Oaks Drive, I just made that up.
right.
I could have GPS coordinates, right? But I'd rather use a name for my place.
So then what happens when you delete something that was in that sequence, does it file everything forward or?
No, it's not going to move the question is if something gets deleted, are things going to be moved around? Not really. It may free that up. It may write some zeros to that specific spot. It might be that it gets reused, but nothing's going to shift around. Because if it all shifted around, then suddenly all the variables have to get updates to where they're pointing to. And they don't want to do that. X is supposed to be 2 million and keeps being 2 million so that every time we write a value to X, it's consistent. Okay, so every variable has 4 parts. It's got a name, a value, a type. Well, what does type mean? Well, that variable could be a number. It could be 32. It could be a string. A string is a series of letters, like the word Jeff. There are other kinds of data too, right? It could be a floating point number instead of a whole number. Now, weirdly enough, those are stored completely different in computer memory, right? You have integers and you have floating point values. Integers are the whole numbers. Floating point values are numbers with decimal points, and the chips handle them completely different. The math involved in doing integer division when you divide a whole number by a whole number is completely different as far as the chip is concerned from doing floating point division. Even if you think the result's going to be the same, right? 4 divided by 2 is 2. 4.0 divided by 2.0, they look the same, but they're handled by different parts of the processor. One gives you an integer as a result, and the other gives you a floating point number as a result. And so that is a type. The type could be an integer. It can be a floating point number, which I'm just going to abbreviate the term float. Am I ignoring you? Do you have a question? Yeah, all right. Or it could be a string. Then there are other kinds of data, right? There's images, and sound files and stuff like that. But fundamentally, we're just going to say right now that we're going to play with integers and floats and strings. What is an integer? An integer is a whole number. A float or floating point is a number with a decimal, or you could say fractional. Why don't I just list these, instead like this? An integer is a whole number without a decimal point. A floating point number, nicknamed a float, is a number with a decimal or a fractional value. Even if it doesn't look like it's got a fractional value, like 4.0, it's still a floating point number just because of that point. And then a string is a series of like typewriter values, right? JEFF, something like that. Anything that the user enters is going to come in as text. So I'm going to say a series of text characters. Yes, sir.
Yeah, something happened here. I hit tab while I was typing, and strange stuff happened, and it the whole thing that was happening out.
Yeah, sorry. Undo.
Or what's going on there.
Okay, good point. If it starts doing that, just see if you can click off of it.
Right, but let's change the words over here. Like,
Yeah,
just ignore
it's
that.
trying to be helpful. And try to type it again now.
There you
Just,
go. I just hit undo. Yes.
sometimes when you're typing, it's going to pop up some stuff when you don't want it to. And I don't even know if I'm going to be able to give an example of that. X equals MAX. Well, it turned to purple. Anyways, you will see very, very occasionally it pop up a little list of things. And those lists of things are programming words that you could then click on and have it fill in. If it pops up that list, just click off of it to make it stop, to get rid of that list until we know exactly what we're doing. And if it does accidentally change what you just typed, then you're just going to click off of it and you're going to edit it. It's trying to be helpful, but it can be annoying. Next time it happens on my screen, because I've already seen it happen once today, I'll point it out very carefully. Not a big deal, just hit escape or click off of it, retype what you're working on. Okay, so those are our 3 types. And the last thing that a variable has is that memory address that I mentioned, 2,300,000 whatever. But we don't care about those. We have no idea where it's storing that age or that name. And in most languages, you can't even figure it out. Some languages, like C and C++, were written to, control hardware. And they do allow you to get the memory address and make direct changes to memory via them. But most languages hide the memory address. Why? Because if you tried to change a specific memory address, you could crash the computer. Our program's not supposed to be able to crash the computer. Even if we write a bad program, it's not supposed to crash the computer. That's just incredibly rude, right? So these are the three parts of it that we care about. We really care about names. We really care about the values, right? Age. The value could be 32, and the type is integer. We don't care what specific byte it's stored in. We don't care about the format in which it's stored in, right? We don't care if it's stored in zeros and ones, or if it's, saved to an SD card, or we don't care anything about that. And then there's the memory address. So let's give ourselves some examples. Name equals Tony. What is the name of the variable? Well, what's the name of the variable? Name. What is the type? It's known as a string because it's a series of typewritten characters. It has those quotes around it. What is its value? Its value is Tony. What's its memory address? Who cares? I'm not going to even list it. We have no way of knowing. Age equals 32. The name of the variable. What's the name of that one? Somebody's listening and looking at and just not saying. What is the name of the variable we just created with that line of code?
Age.
Right. Age is the variable name, right? What is its type? It's a whole number, so it's an int, an integer. And then its value is 32. And one more. Temperature, which I'm just going to call temp, is equal to 98.6. Name of the variable is temp. The type of it is float, floating point, just because of that decimal point. And then its value is 98.6. And again, it's got a memory address, but we don't know. Computer knows. Every time the program runs, it may wind up being a different memory address, but we don't care. We may need to stop and take a short break. We've been here for an hour and almost 15 minutes. Why don't we do that? It'll also give me a chance to try to get the book set up properly. So let's pause, use the bathroom, grab food, whatever we want to do. Alrighty, I'm actually almost getting tired of going through the PowerPoint. We might want to actually write some code. Let's go ahead and do that. Now I do want y'all to follow along if you want to. So we're going to do something fancy. We're going to draw some stuff on the screen. And that would be incredibly hard, except there's a library that makes it easy to draw stuff on the screen once you know the correct syntax. Libraries are good. If I had to invent the internal combustion engine, it'd be a real drag. But if I had a library of material showing me how to do it, I could do that. So, make sure that what you type is not green. Make sure that before you start typing anything, if you run the module, if you have been typing notes, that it doesn't produce a syntax error. Oh, great. I do have a syntax error. I'm glad I checked. Probably have something way down at the bottom of the screen. Yep. Glad I checked. Okay. One more try, run module. Yeah, I'm just making sure that it's not supposed to do anything, but I've validated it so that otherwise I just have to start fresh. Okay, the library that we're going to use today to draw something on the screen is called Turtle. Import Turtle. What is Turtle? Well, back in the 70s or something like that, somebody wanted to invent something to help people, like especially kids, learn the idea of programming. What he came up with kind of looks like a BB-8 Sphero toy, right? That you could buy a couple of years ago. I got excited about. This is the so-called turtle. It's got a pin in it. The pin can lift, the pin can extend. You put this thing on a great big sheet of paper, and with your program, you tell it, go forward 3 inches, turn right 35 degrees, go forward 10 inches, turn right, turn left, right, and then it draws a picture, right? And so the students could learn how to program based on making it draw pictures. That was the turtle. Now, we don't have a mechanical turtle. We're way more awesome than that. We are going to do this with a program. We're going to import the turtle module. We got to create the turtle variable, right? Otherwise, we don't have anything on the screen we can create, we can draw with. Now, this is a very specific syntax, and it's got a capital letter in it. So if you get it wrong, it's not going to work, which is okay. We'll fix it. But okay, what am I going to call my turtle? I'm going to call it Fred. Fred equals, and if you give it a different name, that's fine. You just have to use the same name everywhere. It's like names don't matter to the computer. They just matter to us. Like, right? I could call my turtle that, and it would work just as well as long as I use that everywhere. I could call the turtle Leonardo, Okay, Fred equals all lowercase turtle dot uppercase T, turtle, parentheses in parentheses. Now we're going to make our turtle draw something. Fred dot forward. But if I type forward, half the times I'm going to leave off the R. So I'm going to abbreviate that just because the library supports it to Fred.fd. And I want it to go forward 100 pixels. And I'm going to make a comment here that this is the same as Fred.forward. Because if you're looking up code on the internet, they probably use the whole thing. It's just we happen to have the abbreviation, so why not use it? Save ourselves some typos. Now it's going to run. Now it's going to do something. It's going to draw. So with 3 lines of code, we drew something. That's pretty neat. Let's make it draw something else. Let's tell it to draw a circle. So next line, Fred.circle. No abbreviation. Fred.circle. 200. And it did it. Kind of a big circle, but it drew it. You can see kind of the power of modules, of pre-existing libraries. It would take us a heck of a long time to figure out how to put a window on the screen and to make it do all the pixels. Fortunately, somebody's done that heavy lifting. We're allowed to use it. We're allowed to stand on the shoulders of giants. Well, that's kind of lame looking, but we got it working. We got it drawing something. Anybody getting syntax errors at this point? Do not be shy, because I would like to get it working for everybody. We're all good? All right. So a line with a circle is kind of boring, but there's something I could demonstrate about it. We could change the speed of the turtle so that it draws real slowly or so that it draws real fast. I'm adding this line, Fred.speed, above the forward command. So I'm inserting a line here. Fred.speed 1. That's the slowest speed. Now when I run it, right, it's going real slow. Now that's kind of boring. 10 is almost the fastest speed. So I'm going to change that to 10. But, well, okay. It's not even that much faster. Drawing the circles takes the longest amount of time. The absolute fastest speed is to set the speed equal to 0, and it draws it instantaneously. And that's no fun. I want to be able to watch it. I'm going to set it back to 10, but I'm going to get rid of these 2 lines. Well, you made us type it. Why are you getting rid of it? Okay, well, just because we're so proud of them, we're going to comment them out by adding hashtags in front of them. Now they don't do anything, right? They're no longer part of the programming as far as the computer is concerned. As far as we're concerned, we can still see it. Okay, why don't we draw a triangle? A triangle is going to have 3 left or right turns and then 3 forward commands, right? The turns are for the angles, the corners, and the forwards are draw the lines. So let's go forward. Fred.fd parentheses 50 or 100 or something. And then I'm going to turn left. So he'll start. One thing to notice is that in Turtle Land, for some reason, 0 degrees is what we would consider east. Whereas you probably know that on the compass, 0 degrees is, going up to the north. But we don't really care about that. Okay, so now I'm going to turn to the left, and it's going to start kind of going up. So Fred.left. If we're going to draw a square, it's 90 degrees. So let's draw a square first. Right, now we can see that the turtle is pointed, 90 degrees. It's kind of making a right angle. And it hasn't done it yet. But I want it to turn 4 times and to draw 4 lines. I'm incredibly lazy, so I'm going to cut and copy and paste. You see those 2 lines? I'm just going to highlight them. Now you can choose Edit, Copy, Edit, Paste, or you can right-click and choose Copy and Paste, or you can learn the keyboard shortcuts. For today, I'm going to highlight these 2 things. Right-click, choose Copy, hit the Enter key to go to the next line, be right there, and then hit Paste. And I'm going to do that 3 more times, be right there. Now I'm hitting Control-V to paste. I'm fixing it up. I'm adding blank lines. You don't have to do that, just so that we see that there are clusters of 4 of them. And as soon as I hit run and I see the square on the screen, I'm going to come help y'all. All right, it drew a square. So here's our program so far. I am going to remove these comments just so I can get more stuff on the screen. Then I pause it. How about a triangle? Oh, by the way, some of the mistakes I helped with, it's just so easy to make a typo and not see it. But don't type this because I'm going to erase it. But if you had Fred.Searle, right, you could stare at that for a long time and not see it. Here's something a little bit more subtle. What if there was like an extra parentheses up there? And and on your screen, these things, are the size of ants because y'all have a really small font going on. So I run it, and it highlights this stuff. And you go, what in the world? There's no problem with that line. There's no problem in that line. You could stare at those 2 lines until the end of time and not discover what's wrong with it. Sometimes the problem is on the line above the highlighted lines. And in that case, it is this. What has happened is that it's expecting to see a closed parentheses. Only one closed parentheses to match the one open parentheses that is there. So I fix that, and then these problems go away. So and I'm sure that I'll have to make this comment again, and this has bit me too. You can find an error and stare at it and not be able to figure out what it is, and then you have to look at the lineup of it, and then it becomes clear. Another common mistake is to confuse your uppercase and your lowercase letters. Right, Fred is equal to turtle.turtle. If I made that a capital F, it says name error. Name Fred is not defined. And eventually you'll spot, oh, that was supposed to be lowercase because it is case sensitive. All right, let's make it draw a triangle now. But we're going to get all fancy and make it loop to draw our triangle, right? Because I don't have to copy and paste these lines if I can tell it to start repeating these statements. So here's what I'm going to do. X equals 1 while x less than or equal to 3. Why? Because it's going to have 3 sides and 3 angles. Colon. Then I'm going to hit enter, and this next block of code all needs to be indented because it's inside what's known as the while loop. Now we're probably not going to hit while loops, for another 2 chapters, but that's okay. I like showing y'all stuff early. That way, even if you drop the course, too bad I taught you something. No, I'm kidding. But I like to show you stuff, and then you see it later on in the book, and we talk about it again, and by then, it's lickety-split making sense. All right, so we're going to turn right. Fred.right. Now, triangle, if it's a perfect triangle with 3 equal sides, it's 120 degrees. Now, I made it turn right, but I could have made it turn left, just like the other one, right? It doesn't matter. And again, I'm going to go forward 100 pixels. I don't think this is going to look like how I want it to look. I'm going to make that go right. You can always change these things. All right. And then Fred.fd, 100 pixels. Now, I'm not going to copy and paste. In effect, the computer is going to be doing the copy and pasting. X equals x plus 1, because otherwise x will never increase and it'll always be less than 3, and it'll keep drawing it forever. And I'm going to put a little comment here saying end while. That is not necessary, but it's the end of a block of code, so I'm happy to put a little comment there, just a note. You remember when I was showing you those curly braces, and I had a curly brace, at the beginning of it and a curly brace at the end of it? Marks, it does the same kind of thing. Now don't put curly braces in your code, so I'm going to delete those. All right, there, it drew our triangle. If I wanted it lined up exactly underneath the square, I should make it go forward before I turn, which I think is how I did the square. I think my square went forward and then it turned, but my triangle is being drawn by turning first and then going forward. So if I reverse the order of those 2 statements, it'll move that triangle to underneath the rectangle, the square. Okay, so I'm going to cut that. Come up here, paste that. Now change the order. It's going to go forward, and then it's going to turn the angle, and so it's going to look more like what I wanted it to. Now, if we were really, really, really awesome, we could make it so that all of this was in a loop, and then it would draw the triangles on each side of it. Well, we're not that awesome. I don't feel like doing that, but I'm going to try to make it draw some kind of flower or something with a whole bunch of circles. And then I'll pause and make sure that everybody's got it going. All right, one more while loop. X equals 1 while x is less than. Let's get super fancy and let our program have different numbers of circles and stuff like that. So we're going to create a variable that has the number of times it's supposed to turn. So underneath x is equal to 1. What am I going to call it? Petals, circles. People always misspell circles, but I'm going to go with it. Circles is equal to, well, let's start off easy. 4 circles. And then while x is less than circles, colon. And by the way, I'm putting way too many spaces in. You don't have to put in spaces, right? Well, sometimes you have to. What if I deleted that space between while and x? That breaks it. But we could take those spaces out. If you think it's prettier without, that's fine. Okay, now where did that 90 degrees and that 120 degrees come from? How are those calculations made? It's math. A circle has 360 degrees in it, and so if it's a polygon, all the angles have to add up to 360. So if it's a triangle with 3 sides, it's 360 divided by 3 is 120. That's why we did the triangle with 120 degree angles. It's a square, it's got 4 angles, 360 divided by 4. If we wanted to have 8 sides, it would be 360 divided by 8. Well, I'm trying to make it so that just by changing this number, we change the shape. So I'm going to make the angle that we turn equal to 360 divided by that value. So we're going to calculate that. We could even calculate it here. So above that while loop, I'm going to say angle equals 360 divided by circles, the number of circles. We only need to make that calculation once. That's why I'm taking it outside of the loop and putting it there. If it was inside the loop, if it was indented inside the loop, it would make that calculation every single time. And that would slow the program down a little bit. Now in this case, it doesn't matter whether it would run slowly or not, but we're trying to do good programming style. Okay, let's draw a circle and then turn a little bit. So Fred dot circle, parentheses, angle. No. Let's pick our size. The smaller the circle, the faster it draws, so I'm going to make it 20. And then Fred dot left, our calculated angle. So Fred dot left, parentheses, angle in parentheses. And then we have to add 1 to x, just like I said. What happens if I don't add 1 to x? Let me show you what I'm talking about there. Yeah. Okay, I'm getting tired of watching that. So that's an infinite loop because I did not change the value of x. So x is always less than circles. So x equals x plus 1. And I'm going to back tab and add my end while. And it only drew 3. I've made a mistake in my programming. This should be x less than or equal to circles. That was not an intentional mistake. But since circles is set to 4 and x is 1, while 1 is less than 4, draw it. Okay, great. Add 1 to it. That's 1 circle we drew. We added 1 to x. 2 is less than 4? Yeah, sure is. So it draws another circle. Now we've drawn 2 circles. Add 1 to ed. Is 3 less than 4? Yeah, sure is. Draw another circle. Okay, now we have 3 circles. Add 1 to x. X is equal to 4. Is 4 less than 4? Well, honestly, it's not, right? 4 is equal to 4. It's not 4 less than 4, so it exited the while loop. That's why we only got 3 circles. So I need to change that to x is less than equal. And now it'll draw the 4. All right. One more change. Let's draw a lot more circles than that. I don't know if kids play with spirographs anymore, but it used to be you could draw something, you know, with put down plastic circles and do that. Let's draw, I don't know, 16 circles. So I changed this line to 16. And remember, if you get tired of it drawing so slowly, go back and change that dot speed command to have a 0 in it instead of a 1 or a 10 or whatever it's set to right now. Kind of looks like a slinky. All right, gonna wander around, make sure everybody's doing good. But first I'm gonna change the speed. You know what? We don't have any patience anymore. I'm gonna find my speed command and change that to a speed of 0, which means remove all delay. That's the fastest possible speed. Light speed. Okay, cool. Now something that would have been good is if we had stored this radius here in a variable, right? Because changing that variable would change the size of it. I'm just going to change that to 10, and we're going to see that our circle is itty bitty, so I change that Fred.circle to a smaller value, right? Or I can make it a larger value, right? I could make it 100. We could even ask the user for these values before we start drawing it. How many circles do you want? Since it's drawing them nice and fast, I'm going to say that I want 360 circles. Now, this is going to look stupid. It ought to be just a big old black blob. No, that's kind of cool. I'm digging it. Taking a long time. I'm sure I'm glad I set my speed equal to 0. All right, lastly, and then as promised, I'll wander around and make sure nobody has syntax errors. Let's change the color of the pen. So before x is equal to 1, we're going to do Fred.color, parentheses, quote, and I'm going to pick a new color, purple, end quote, end parentheses. Just going to draw that in purple. There's other things we can do. It has a pin up command or a lift command so that it's not drawing as it moves. It has a fill command so that you can draw a square and then fill the square with a color. Stuff like that. It's got a move command that'll move the point from one place to another. It's got an angle command so that you can set its angle absolutely rather than just say left or right. You could change its heading to a very specific angle. We'll play with turtles just because I think it's a fun way, a good way of learning some concepts. Like, for example, we've already learned the idea of loops now. All right, now we're going to go off on just a little bit of an adventure because we're going to try to see if we can get it to draw a spectrum of circles, you know, colors. Well, what is the syntax of the turtle color command? That's not what I wanted. Okay, Python turtle color. We're using Python 3, so I'm not going to click on the Python 2 documentation. I'm going to click on the Python 3 documentation. Hey, that's cool. Okay. The only color I know how to make it do is to shift it from black to white. So we're just gonna go with that. So we need a color command here. Firstly, let's change the number of circles we draw to 255. There's a reason I'm picking that number, and I'm not going to even explain it. And now, so I just changed that line. And here, I'm going to set my color equal to something that looks very strange. Fred.color This is going to look stupid. I'm really sorry, guys. I hope it works. I'm going to copy this variable and paste it because I don't want to have to type in circles 3 times and make a typo. So Fred.color, parentheses, parentheses, paste, comma, paste, close parentheses, and I hope that this works, but I've never tried it before. Boom. Didn't work. Bad color sequence. Don't type this. We may have to punt on this, but I sure would like for it to work. See, there's the syntax for it. Alrighty. One more attempt, and it's going to look complicated, but I don't mind showing y'all something complicated. And it's going to be pretty lame. It's only going to have like 4, 5, or 6 colors in it. So instead of circles is equal to 255, we're going to add a list of colors up here. So instead of Fred.color purple, I'm deleting that line, Fred.color equals purple, and I'm going to say colors equals, and I'm sorry for this weird syntax, you don't even have to do this if you don't want, square brackets, which are the ones next to the letter P without shifting, colors equals square brackets, quote, red, end quote, comma, Roy G. Biv. Orange, end quote, comma, quote, green, end quote, comma, R. Red G. Quote, blue, end quote, comma, indigo. Is that a valid color in this language? I don't know. End quote, comma, quote, violet, end quote. I forgot yellow. All right, yeah, and you said that 4 times, and I ignored you every time. Sorry about that. Red, orange, yellow needs to come before green. There. They all have to be separated by commas. Mine is at the end of the list, right? I'm going to put a return there just because it was going off the edge of my screen. You don't need to do that, right? So don't do that, but I did it. All right, now here, where it says Fred.color, I'm going to erase that line because I'm going to kind of retype it. Fred.color, parentheses, colors, open square bracket, X, close square bracket, close parentheses. I hope it works. Sorta. It started working. Sorry guys, we got a couple more changes to make. Change this X equals 1 to X no, here's an easy way to change it. And I'm sorry it's not perfectly easy to understand. Change that X inside the square braces to X minus 1. And it seemed like it was malfunctioning. Okay, it was. So sorry to make all these changes. Here's the line that we added, right? And now I'm going to change this circles line from 255. Oh boy. I guess this will work maybe. To LEN, parentheses, not square braces, colors in parentheses. Why are we doing that? Because we're setting this number of circles equal to the number of items in this list. So since there's 6 or 7 items in that list, then the number of circles is going to be 7. And if we went in here and we added some more colors, chartreuse and beige and things like that, all right, kind of drew our little multicolored thing. If I made the size of the circle smaller, the colors might be a little more emphatic, so I'm going to change Fred.circle down to 10. And that's kind of boring looking though. 50. All right. It's possible that it's working on your screen. It's also possible that I made so many changes and you weren't able to keep track of them all. You know, not your fault. So let's pause it, see if we got it going. And we're probably going to end class real soon. So we've pulled up a list of colors. I'm just going to add a couple more colors to our list, and then we're going to add a fill command so that our petals are solid colored. Alrighty. Alright, so along with these colors, after violet, I'm going to add a couple more. Sky space blue, green 3, not greed, green 3. I'm just picking colors from this list. And the way I got to this list is I typed in to Google TKINTER space color space list, like that. TKINTER color list. That's how I got the list of colors. And then I searched on images and I picked one. All right, maroon looks like a good color. Navajo white 2, and quote, cadet space blue. I wonder why some of them are separated by spaces, but Navajo white and steel blue are not. All right, anyways. I just picked some colors at random. Yeah, that's pretty cool. I'm glad you asked about the colors. That's pretty cool. All right. Lastly, I wanted to fill in the petals. So before we start drawing the circle, we're going to add a begin fill. And after we start drawing the circle, we're going to add an end fill. Now, unfortunately, I don't remember whether we have to use underscores or not. So, turtle begin underscore fill. That looks right. Google kind of suggested that, right? As I was typing it. So it's got an underscore. You never know. Okay. So, before Fred.circle, I'm going to add Fred.begin underscore fill, parentheses in parentheses. And after Fred.circle, we're going to do Fred.end underscore fill, parentheses in parentheses. Start your filling and then stop your filling. Cool deal. I'm kind of happy with it. If you didn't like it like that, if you want it the other way, then just delete those lines. Not much. Just our triangle and our square stuff. So I'm going to scroll it back down because I'm expecting everybody to have the square and the triangle working. All right, why don't we call ourselves done for the day? I think it's about time anyways. I need to make a Dropbox for this. Forgot